Have you ever figured something out and you try to explain to someone but they just didn't believe you? Well, this happened to a man named Eugene Parker, who in 1958 wrote a paper about the solar wind. To start at the beginning, Parker's theory came about between a confliction of two earlier pioneers, Biermann and Chapman. Biermann theorized that the sun expels radiation in all of its directions, at least nearby. He determined this by observing comets that would go around the sun and noticed that their tails would always point perpendicular away from the sun's surface. Chapman theorized by calculation that the sun's corona, or its outer atmosphere, would retain more energy than it would lose by radiation, meaning that it must expand, envisioning a sort of static solar cloud that would encompass our entire inner solar system. There was a problem, however. The problem was that Biermann's radiation would have been easily counteracted by Chapman's solar cloud. But we know that radiation affects comets. Well, in 1958, Parker had a solution. The solution was that the radiation and the cloud were in fact one and the same. But what he also found is that this cloud was not static, but expanding at a supersonic rate. This would eventually develop into his theory of solar wind, but in this paper, the name solar wind is not mentioned once. There was a bigger problem, however. The problem was that we had very little data about our own sun. These papers were produced with smooth, idealized models. In fact, the last sentence of Parker's paper was a direct warning to the reader about how limited their predictions were. It made it very difficult for Parker to publish his own paper because, well, he didn't have the evidence to prove it. Enter the Mariner 2. The Mariner 2 was launched in 1962, and it was the first successful spacecraft to encounter another planet. It spent 4 months orbiting Venus, but it also was equipped with the ability to track this theorized solar wind. In its 4 months, it was able to confirm that there was a flux of plasma that radiates from the sun, and it was able to record its velocity, density, and its temperature. It was very lucky for Parker that this satellite essentially completely confirmed his theory, only just 4 years later. In 1965, Parker redefined his theory, formally naming it the solar wind. In his analysis, he found that the corona actually does mimic a normal atmosphere, at least till some point from its surface, of which then the wind is released and escapes, diffusing across the entire solar system at supersonic speeds. The collision of the particles within this wave is so intense and creates so much energy that, in fact, it maintains a relatively constant temperature and velocity throughout, likely caused by the wave dissipation of these Alfvén waves, which means they transfer their mechanical energy directly into heat. On the surface of the sun, there are these small-scale filaments that burst and fuel the solar wind. Most are too small to be of any problem, but occasionally large filaments called mass coronal ejections, and alongside them solar flares, could be so massive that they can go as far as to Earth, damaging our satellites and our electrical grids. But they also produce our northern and southern lights, and for the most part, are not a major problem because of our Earth's magnetic sphere. The same can't be said for Mars, however, who likely lost their oceans because of the sun's coronal ejections. This here is a list of all the satellites that have made it their primary mission to analyze and study the sun and space weather. As you can see, most of these are fairly recent, many just after 2000. But the most recent one was launched a little over a month ago, the Parker Solar Probe. The Parker Solar Probe was launched with the main mission to get as close to the surface of the sun as it possibly can. It will be the first NASA mission to touch the sun, traveling as close as 4 million miles from its surface. For reference, the distance between the sun and Mercury is like 36 million miles. This here shows you the orbit mission of the probe. It will go along this orbit for the next 7 years, and you can just see how close it will be getting to the sun. To protect against the sun's immense heat, a large shield will help in reducing the immense heat that's being produced by the sun, reducing the 2,500 degree surface temperature to like 600 degrees behind the shield. A water cooling system would then be used to reduce the temperature from 600 down to a cool 80 degrees. With the Parker Solar Probe, we're finally getting involved with our sun, setting a precedent that people like Parker, Bierman, and Chapman have been waiting years for. A precedent that we can expect more from the future. Thank you very much.
That was your fastest one yet, 5 minutes and 33 seconds.
That was great,
That was
Mason.
great.